Okay everyone, so this is actually lesson 3 of structure and bonding. I decided that it would be too much to put in one lesson to cover all of these things. So in the previous lesson, lesson 2, we looked at polar molecules, how to determine whether a molecule is polar or non-polar overall. And in this lesson, we're going to begin looking at intermolecular forces. We're going to start with a general introduction, then we're going to look at London dispersion forces and permanent dipole interactions. It's a bit of a mouthful, but it is what it is. And then after that, in the lesson 4, we're going to look at the third type of intermolecular force that you need to know about, which is hydrogen bonding. So, intermolecular forces, these are super important in chemistry. They are relevant to all sorts of different types of chemistry. In particular, if you're interested in medicine, then intermolecular forces are particularly important in the action of biological molecules and proteins, the action of enzymes in the body, also in the way we design pharmaceutical products. So intermolecular forces are a huge area in chemistry. The key thing to remember about intermolecular forces is intermolecular means between molecules. So, if I have two molecules, say 2 molecules of oxygen here with a double bond, I am talking about the forces between separate molecules, not the strong covalent bonds which hold the atoms together within molecules. So, it's really, really important that you don't get mixed up. Intermolecular forces means between two separate molecules. An example might be, the only example I can think of is if you go interrailing, you are travelling between different railway stations. That might be one way of remembering it. See if you can come up with a different way of remembering it. So intermolecular forces are the forces between molecules. We have covered this a few times already. And they are also known as van der Waals forces. Now I've drawn my W a bit strange there, but anyway, van der Waals forces. You see both come up in papers. The main reason you might use van der Waals forces as opposed to intermolecular forces is if you're talking about monatomic elements, because technically the noble gases are made of atoms, so it probably isn't appropriate to refer to intermolecular forces. That might be a case in which we refer to these forces as van der Waals forces. But in this part of the topic, we're not really going to be considering the noble gases, we're mostly thinking about covalent molecular substances. So, here's a little introduction. Covalent molecular substances can be solid, liquid or gas at room temperature. And you probably know a lot of different common examples. So solids, sulfur is a yellow powder you might have seen in chemistry. Wax, just ordinary candle wax is a good example of a solid molecular substance. Butter would be another example, fat, lard, all these things. Liquids, you've got hexane, again a solvent that we would use in the lab, but then really common everyday things you've got at home, oil and water are also molecular substances. And gases, oxygen, methane, there's loads and loads of different examples again. So just like we learned in the first topic, and we learned when we learned that the noble gases, even though they're gases at room temperature, they can still condense and freeze. So this is true of all molecular substances. Even the ones that are gases at room temperature can condense and then freeze if we cool the temperature down. And this tells us that there must be forces which attract the molecules together in all substances. And what we're going to start off by considering is we're going to go back right to pretty much first year science, and we're going to draw some particle pictures to show how the molecules are arranged in solids, liquids and gases. We'll just represent a molecule in general with a circle, although obviously we know molecules have lots of different complex structures. So remember, in a solid, our molecules, or whatever particles, if this was a metal, it would apply to the metal atoms as well, or the ions in an ionic substance, but we're imagining these circles in this case represent molecules. So in a solid, our molecules are arranged in a nice regular rows. They are touching each other, they're very close to each other, haven't drawn them quite touching, and they are not able to move freely, but they are vibrating. So particles always have some level of motion. The only temperature, and the level of motion is to do with is to do with temperature. So the hotter a substance, the more kinetic energy, the faster the motion of the particles. So that's something we'll look at more detail when we look at the reaction rates topic. So the particles in a solid are close together, they're arranged in a regular pattern generally, and they are vibrating. What happens as we heat a solid up is, let's go back to solids for a minute. Particles are held closely together in a solid because there are these forces which attract the molecules together. As we heat a solid up, what happens is the molecules get more and more energy, and eventually the motion of the molecules becomes stronger, becomes more, outweighs, you could almost think, the attraction between the molecules. So eventually we'll get to a point where our molecules are still pretty close together. Some of them, they are still touching each other, but they're all higgledy-piggledy and they can now move around freely. So there are still forces of attraction between the molecules in the liquid state, otherwise they wouldn't stay together. But we have given the particles enough energy that their motion overcomes the tendency for them to stick together in a kind of rigid block, and the molecules can then move around and flow around each other. One thing that's really, really, really important to remember is it is not the atoms which come apart when this happens. The atoms in the molecules stay stuck together, the covalent bonds do not break. We are just disrupting or breaking slightly these intermolecular forces, but they're still there. Finally, once we heat the substance up even more, as we heat the substance up, the particles are going to be moving really quickly, and our gas is made up of really fast-moving particles. So I've drawn these slightly bigger arrows, and the gas particles will move in straight lines in all directions until they come into contact with, say, the surface of a container or another particle, in which case they'll bounce off. So they're bouncing around all over the place. In a molecular substance that's a gas, the motion has completely overcome the attraction between the gas particles. So the molecules are now moving so fast that when they come into contact with each other, rather than kind of clicking together, they will just bounce off each other. If you can imagine sometimes you might see a gate that swings back and forward, and only when it's swinging at just a sort of slow speed will the gate just click into the latch. When it's moving really quickly, it just pings back and forward. So it's a similar thing with the gas molecules. There still is the potential for intermolecular forces between them, but when they're moving very fast, like they are in a gas, the molecules tend to behave more as sort of rigid spheres and bounce off each other. So I'm going to leave you to label these arrows with melting, freezing, etc., because I'm sure you are very capable of doing that. So what the notes say now is when we heat a solid, energy is taken in by the molecules and is used to break the intermolecular forces which hold the molecules together. So when I say hold the molecules together, I mean hold one molecule beside another molecule, not the forces which hold the atoms together in the molecule. When heated enough, the forces are broken sufficiently to allow the molecules to move around and form a liquid, and the higher the melting point means more energy is required to overcome the forces. The same thing applies to going from liquid to gas. So when we go from liquid to gas, the stronger the forces between the molecules and the liquid, the more difficult and the more energy is required to put in to break or overcome these forces and allow these molecules to become separate into a gas. So the really important thing to remember in this whole topic is the higher the melting and boiling point of a molecular substance, the stronger the intermolecular forces. And that applies, that's always the case for a molecular substance. So, question 1 just says, use the Databook to find which substance has the stronger intermolecular forces. So you just need to use this rule here and the Databook to answer that question. Right, in case you had no idea where to start with question 1, I'm just going to give you a little hint before I reveal the answers. So I said use the Databook. I wasn't that clear about what you should use the Databook for. But hopefully from the top sentence, we said the higher the melting and boiling point of a molecular substance, the stronger the intermolecular forces. So you might have inferred from that you need to use the Databook to look up the melting and boiling points. Now, just to make it extra tricky, I haven't given you page numbers or anything, so you might have to use the contents page to look up the melting and boiling points. Now, another fun aspect of it is that you might need to know whether what you're looking for are elements or compounds, because the melting points and boiling points are on different pages. So hexane and octane, hopefully you're remembering that those are hydrocarbons, and they will be on the page which is about melting and boiling points of selected organic compounds. So see if you can find that in the contents page. In fact, oh, I'm being so kind to you. Look, here's a look at it just there, so you can see hexane and octane there, hopefully. So what you need to do is look and see which has the higher boiling point or melting point, and therefore which has the strongest intermolecular forces. On this page as well is part C, butan, methanol or butan 1-ol. So hold on a second, I'll show you that there. We've got methanol and butan 1-ol both on the same table there. And then for the part B, you need to look up the melting points and boiling points of helium and nitrogen. Now, just to be nice and helpful, those are elements and they're on a different page of the Databook. But again, I'm going to be really kind to you. If you didn't get that already, here they are here, so you can take a look. So, to figure out which substance has the stronger intermolecular forces, you just need to look at the melting points and boiling points. Your answers should be octane has the stronger intermolecular forces in part A, nitrogen in part B, and butan 1-ol in part C. So, this topic's been an introduction to intermolecular forces in general. What we're going to look at in the rest of this topic, or what's going to be important in the rest of this topic, is considering the 3 main types of intermolecular force separately. So, we have got 3 main types of intermolecular forces in chemistry. Actually, I'm not going to spring any more out of the woodwork when you do advanced higher. This is as in depth as it gets pretty much when it comes to intermolecular forces. So you're learning at higher almost the real truth in chemistry, which is quite unusual. So the first type of intermolecular forces, which we looked at a little bit in topic 1, are London dispersion forces, and these occur between all molecules. That's a really, really important thing to remember. The second type that we are going to look at are called permanent dipole interactions. Now you can, like I say, that was a bit of a mouthful, and you can abbreviate that to PD to PD, but it's really important that you still say interactions. Okay, you must, if you're abbreviating the permanent dipole to permanent dipole bit, you must still include this interactions bit. It's an important part of the kind of definition of the word. So permanent dipole interactions we'll look at in a little minute, and these occur between all polar molecules. So in the previous lesson we learned how to figure out whether a molecule was polar or non-polar. While we're on the subject of abbreviations, you can write LDFs in replacement of London dispersion forces. In an exam, I think the SQ would accept that. I would always prefer, though, if you are doing an abbreviation in chemistry, that you write the whole thing out first. So in whatever you're writing, the first time you write it, you would write out the whole thing, London dispersion forces, and then you would put LDFs in brackets, and that just indicates that whenever you use LDFs, you're talking about London dispersion forces. That's just a little bit of a more a professional way to do it. Okay, and then the third type of intermolecular force is hydrogen bonds. We're going to learn about those in lesson 4. They are a special type of permanent dipole interaction when we have OH, NH or FH bonds in a molecule. Hydrogen bonds are particularly important in biology, and if you do biology, you will come across hydrogen bonding as well. So, what we're going to do is we're going to look at each of these forces in turn, and we're going to consider their relative strength. What you've got to remember is all substances have London dispersion forces. And what you should be able to work out is whether they also have either permanent dipole interactions or hydrogen bonding. So you should be able to do that by the end of lesson 4. So this is one of the key points of this topic. London dispersion forces may be the only type of intermolecular force. But you may also have either permanent dipole interactions between the molecules or hydrogen bonding between the molecules. So part of what we're going to look at in the next little section is how you tell whether they have these different types of forces, whether the molecules of a substance have these different types of forces, and part of what we're going to look at is the relative strength of the different intermolecular forces.